Thank you, Alejandro. Buenos dias, everybody. I'm going to switch to my native tongue, make sure everything gets across clear. But thank you for the time. Really interested in getting, talking to you guys and about ultrafiltration, but also not just including the products, but how they're applied and the importance of that, and looking at total cost of ownership in particular, and utilizing process economics to make the best change out decisions and best process decisions that we can make, focusing around ultrafiltration and other separation processes within the ecoat process. So just a little ground rules as we start. This will be basically about 45 minutes of content, and we'll have about 10 to 15 minutes for discussion and questions at the end. Do like to have interactive sessions. They're always better to get people engaged. So definitely encouraging questions, and you can do that either by typing into the chat box, and that'll make sure that the questions are captured. So that would be the preferred way to do it. If there is an immediate question, we can raise your hand through Zoom, but please keep your microphone muted if you're not speaking. Sometimes there can be some background audio that causes issue. And then, if there's any, like I said, any questions or anything, put them in the chat box, and we'll get to them either at a certain time or at the end of the webinar. So I am Ben Weaver. I've been working with Solecta for about 6 years in operations, sales, engineering roles, and I've had about 12 years of membrane experience. I started in water and wastewater, and then when I joined Solecta, focused in on process membrane applications, including ecoat applications in particular. So Solecta, we focus on microfiltration, ultrafiltration, and nanofiltration, as well as reverse osmosis membranes. But it's really the solutions that we provide around these membranes that differentiate us. So what we'll be talking about here. So number one, we'll be focusing on producer objectives, and we spend a lot of time understanding what the goals and priorities of clients are, because every solution is going to be slightly different and tweaked to each client, depending on their business drivers and their goals of what they want to accomplish. We'll touch on membrane essentials, some best practices in UF. So what are the things that we want to monitor, things that we want to track to make sure that our performance of our UF system is optimal. And then we're going to tie that to total cost of ownership. As I mentioned, we want to look at process economics to make the best decisions. And when we're talking about a large, either an automotive plant or a large parts coating line, it's the UF can just seem like a small cog, and typically can be replaced based on, the flow rate's too low, let's just replace the element. But we want to take it to the next level and really monitor and use data to provide the optimal time to replace elements from a process economics perspective. And then we'll share some client success stories where we've taken this total cost of ownership approach, tied it with the membrane products that we provide, and share what some of our clients have had success with these solutions. So at Solecta, we understand that the membranes are part of a much larger process to create the finished product, and what our goals are to understand the business drivers of each individual company, and make sure that the priorities that the clients have are aligned with the solution that we can provide. And so, if you take a look at the diagram on the right-hand side, that's really kind of a mimic of a plant operation. And we understand that there's a number of different spots that membranes can be used. to improve the performance and improve process economics. But really those tie back to business drivers such as revenue and profit growth that resonates with any company. Anytime you can tell them, hey, we're going to improve revenue, we're going to improve profit, it's advantageous. Working capital, sometimes capital expenditures, it's difficult to find that extra money to increase the system size. If you have an increase in demand, typically that means you need to increase the process steps, the size of the process steps. Well, sometimes that's difficult because working capital is tight. Brand risk, CapEx management, quality. We always want to make sure that the products that we're producing out of the system are going to be quality products that meet or exceed client requirements. And we'll touch on that, especially when it comes to UF rinse and the quality of parts coming from the ecoat bath. Workforce capability when it comes to training, turnover. Want to make sure that we're providing benefits to whether it's training or best practices, audits. Making sure that we're improving the workforce capability, and then it all has to tie into safety. We need to make sure we're doing it safely, and then environment and health come into play. We hear constantly about sustainability needs and metrics that clients need to make. We'll want to make sure that the solution ties into sustainability. These are the business drivers that we have after talking to many clients and summarized in about 7 business drivers. But one thing to think about, what are your business drivers and what are the things that you guys do that maybe separate you and how to what are your priorities when it comes to your business drivers? So who is Solecta? And this is what we consider our value proposition. And it's a 3-pillar value proposition. It's client success and making sure that whatever we do, we're bringing success to our clients. And really what that means is we're focused on bringing membrane expertise and identifying solutions to meet the client operational needs. And so, we really dive in on those business drivers to really understand, what does that optimal solution look like to our clients. Bottom line focus, this is where process economics come into play. Everything comes to cost savings in many places. And that's obviously a big part of it. But is there a way that we can, improve revenue, improve profit? Is there different ways to look at it than just limiting costs? And there's an aspect to limit costs, but there might be bigger aspirations for revenue growth and things like that we look at to take the whole process economics and make the best decision from a holistic point of view. And the third pillar is entrepreneurial partner, and really want to focus on building long-term relationships. Solecta is a little bit of a smaller company. We're nimble, responsive, and we're going to be very creative in our solutions and try to bring something that gives our clients a differentiation in the marketplace. So share about Solecta. Now I want to dive into some of the membrane essentials, specifically around ecoat. So here's a pretty generic diagram of an ecoat process here in an automobile plant where we're coating car bodies, and the car body will go through. Let me bring up pointer. 1 second. So the car body will go through the analyte tank where the paint is adhered, and it'll go through a number of rinse stages before you reach the final rinse, and then before it goes to oven steps in the curing process. But in this process, we've got a number of different places for membranes to help improve the processes. And ultrafiltration membranes have been around in this process for a number of years, 20, 30 years. It's a tried and true technology. But what UF was designed to do was really capture all the paint solids, or as many paint solids as possible, return them to the paint bath so we're covering solids, at the same time producing a very high quality rinse water for the rinse stages. And the benefit of this is that we have a closed loop system through this process. So we have, with the UF stages and taking the overflow from the paint bath, sending it to the UF, and then taking the overflow from the rinse, treating it with UF as well. This is one option for that. It's really saving over 98.5%, over 99% of the paint solids, and then also producing that very high quality rinse water. And so, as a membrane manufacturer, and solutions provider, we took a look at this and said, all right, where else can we expand out in the ecoat stages alone? And that's where we came to FR, and really FR stands for final rinse. And we'll touch on some of the benefits of FR here in some future slides. But just wanted to level set where we're talking about for the rest of the presentation. So we're talking about spiral wound elements here for this application. And when you see a pressure vessel, you may not understand exactly the flow that's going on inside that pressure vessel. And so, this is a diagram to kind of show how a spiral wound element is constructed, and I'll share some of the purposes of each aspect of it. So there's really 5 main constituents to a spiral wound element. You have your permeate tube, and the permeate tube is a porous tube that collects the permeate material that's been transported through the membrane and exits out the top of the element in the case of ecoat. And the other constituents, so you have, as a feed comes in, it's going to traverse along the feed spacer, and then it's going to go through the membrane, and then go into the permeate spacer. So as the feed water comes through in the feed solution, it's going to come through here. You want to have a very, very high cross flow, a feed flow rate, in order to prevent any of the solids from building up in the feed spacer. And also the point of the high feed flow is to keep the paint solids and any other potential foulant in solution. Basically, we don't want them deposited onto the membrane. We want to keep them in motion while they're going through the element. Then the clean water will go through the membrane, collect on the permeate spacer, spiral wound to the permeate tube, and then out of the top of the element. The final piece of this is the outer wrap, and in the case of ecoat, that's going to be a fiberglass reinforced plastic outer wrap, and so that basically gives it the structural integrity to operate at the pressures needed for ecoat processes, and actually it can go even higher pressure at times, but anywhere from 50 to 70 psi is pretty typical operating pressure for the spiral wound element. So when we go into an actual process of it, so when we're looking at the paint parameters for an 8-inch element, so we use 8-inch because that's probably the most widely used element in the market. So we standardize around that, and it's coming into the UF system, and you always want to have pre-treatment prior to the UF, and that's because as we talked about in the previous stage, we don't want to have those solids plugging the feed spacer. And so in order to prevent that, one of the things that we do is we recommend pre-treatment prior to entering the UF module. And typical pre-treatment is a bag or cartridge filter. We always recommend at least 25 micron for our 31 mil feed spacer. So when we say 31 mil feed spacer, that's the thickness of the feed spacer. And so, it's 31 thousandths of an inch. So it's not a very large gap in there. So we want to make sure that we keep the smaller solids from entering, the larger solids from entering the UF module and plugging up the feed spacer. So paint inlet is going to be coming in at anywhere from 38 to 65 psi. That's optimal. And really, we want to maintain a DP of about 1.9 to 2.4 bar. And this delta pressure is very important to monitor and maintain this, because that will give you an indication that your feed flow is adequate to keep the solution, the particles in solution, and so they don't deposit onto the membrane. So we want to create a turbulent flow across the membrane surface. And if you're monitoring that DP, if it drops too low, it's probably indicative of lower flow. If it goes up, too high, it can be indicative of either blockage or pluggage of the process. So it's really a good idea, to monitor that DP as you're operating. And then the paint return, so that's the paint going back to the paint bath. That's going to be at discharge about 10 to 36 psi, and that's really dependent on the system. How far away is the UF system from the paint tank? How many turns of pipe there are. So we want to, that's going to be very, very site specific, but we want to make sure that inlet pressure matches to keep that DP. So that DP is what we're really monitoring here. And then when we're talking about what's produced in the rinse water, so out of an 8-inch element, we're usually looking at 3 to 5.5 gallons per minute of permeate, with a total solids of about 0.3 to 0.4%. So the paint inlet's going to come in, depending on what type of paint, that can range anywhere from 12% on the low side solids up to 20% on the high side of solids. But basically, majority of those solids are remaining on the return side and return to the paint bath, where we have a high quality permeate coming out of it out of the module for rinse water. So when we want to talk about performance considerations and how some of these variables impact the performance of the UF over time. So when we're talking about the variables, number one is paint type, and all the paints are going to act a little bit differently when it comes to filterability of the paint. So the flux effect is going to vary depending on what paint it is, and some of those are going to tie into the specifications of the paint. Some paints require slightly higher solids. For the epoxy paint, you're looking at 18 to 20% solids. Maybe for an acrylic paint, you'd be looking at 12 to 14% solids. So that's going to impact the performance of the UF depending on what the type is, and then what are the specifications of the paint. Paint flow. So this is what we talked about, delta P. So paint flow and delta P are probably the two most critical parameters we want to monitor that impact the performance. And we said we want to keep about 80 gallons per minute of feed flow per 8-inch element, and that can go a little bit higher. We always say higher is actually better for the membrane, because it'll help keep the turbulence of the feed solution in the membrane. However, you don't want to go too high on delta P, where you start impacting the structural integrity. So you are going to have a pressure drop along the length of the element. If that becomes too high, you can have defects due to high pressure, where that's telescoping of the membrane. You can end up impacting the seals. So we want to make sure we're within the range on delta P when operating. We talk paint solids. Like I said, with higher paint solids, you are going to basically foul the membrane a little bit more. So, usually anything higher than 20% solids in the paint bath, you're going to start to see a detrimental impact of the solids. And what that does is the flux decreases, meaning the throughput output of the UF module decreases with higher paint solids. Average pressure, TMP, we consider transmembrane pressure. And that's really the driving force driving the water through the membrane. And transmembrane pressure is the average of the feed and concentrate pressures minus the permeate pressure. And the permeate pressure we always want as very, very low. So ideally we'd be as close to 0 as possible. We never want to have any back pressure on the module. So ideally we'd like that permeate pressure very low. And pretty typical is less than 5 or 10 psi. So that means a majority of that feed and concentrate pressure is going to be the driving force. And the impact on flux over time is if you start with a higher driving force, you are going to drive more water through the membrane initially. But what you're also going to do during that time is foul the membrane a little bit quicker. And so what you're going to do is with a higher TMP, you're going to start with higher flux, but you're going to decrease quicker than at a recommended TMP. So you want to monitor the TMP to make sure that you aren't overfluxing the membrane, that you aren't overfouling the membrane, that we are just maintaining that slight drop in TMP over time. And then once the membrane is cleaned, that's where you're going to bring back the TMP, and it'll come back into normal operation or normal ranges. Temperature. So with temperature is really pretty fixed on the paint bath, usually around 90 to 100 degrees Fahrenheit. But if there are some opportunities, any type of increase in temperature is typically going to increase the performance and flux of the membrane. And part of this is due to just viscosity properties. With increased temperature, you are going to have lower viscosity in the water, so it does make it easier to push through the membrane a little bit. So, and then when it comes to pH, and when it comes to membrane chemistry, typically with an increased pH, you are going to see improved flux performance. Now that's just from chemistry alone. There's going to be other implications for this. For instance, say you add acid to your paint bath to bring the pH a little bit lower. You may actually see an improved performance from the UF system, but it's not necessarily due to the fact that we're lowering pH. It's due to the fact that we're introducing acid to control the foulance a little bit more. So, if we're looking at a clean membrane and you're have it at pH 7 running water through it, if you increase that pH to 10, you're going to have a little bit more flow in a perfect situation. This doesn't take into account foulant interactions, which can impact the flux of the membrane. And then last two, contamination and microbiological, they kind of go hand in hand. Microbiological is a example of a contamination, but any carryover from the pretreatment, whether that's phosphate, whether that can be other transition metals from the pretreatment, that can cause fouling of the membrane. And then, any type of a bacteria attack will cause fouling of the membrane, and both of those will impact the flux negatively, basically decreasing the output and decreasing the performance. And so, we definitely have cleaning formulations that combat, either whether it's a transition metal or a bacteria. So we have the cleaning formulations to really look at those, but the more that we can minimize the contamination, whether from metals or bacteria, the better the UF performance will be. So when we talk to clients and understand, what are some of the problems that they face, kind of day in, day out. And so, this is a list of some examples that we hear frequently. Definitely not a fully inclusive list of everything. And one thing that you could think about is, what are some of the problems that I face? If you share that with us or with Rasch, we'd be able to help and provide a solution with that. But here's a few that we find are pretty common to producers. So number one, not enough rinse water. Either we had the client had to increase the capacity, the throughput of the system, which required more rinse water, or maybe their performance of the elements are not as good as what they expected. Basically, we're not producing enough rinse water, and the impact of that, it limits capacity. And I always say that if we're limiting capacity due to rinse water or not enough rinse water, get Rasch or Solecta involved, because there's a pretty quick solution to that. Maybe requires a little bit of capital, but when you look at the overall economics, it's really a no-brainer to either improve the capacity of the UF system. If you look at the holistic economics, the process economics, the UF is pretty minimal in the grand scheme of things, and so you don't want to limit your system due to rinse water of the system. Another complaint we hear is defects on the car body. You know, as it's going through the rinse stages and then goes into the oven, we may see pitting, we may see denting, we may see, you know, just any type of defect on the body or part itself. And really, it's a poor coating quality. And really, some of the potential root causes could be, you know, there might be excess paint in the permeate, whether that's, you know, whether the membrane is leaking a little bit, or maybe it's not the proper membrane selected for the application. You know, there's quite a wide range of pore sizes that are used in the ecoat market. And so, you know, there's opportunities that if there is too much paint in the permeate, that, you know, we can look at alternative products to improve the quality of the permeate and improve the coating quality on the body. Another issue that we hear about is we're cleaning too frequently. We're using too much chemical, we're using too much water, we have increased downtime, and that's preventing us from producing you know, enough rinse water. And really, this can be tied back to, you know, is there contamination in the system? Are we fouling up the membranes too quickly? Really looking at operating parameters to identify what's causing the membrane to foul up quickly and require too frequent CIP. You know, typically it's going to be either a contamination issue or the solids in the paint bath. But really, you know, we want to look at all options there to understand, you know, what is really causing the frequent CIPs in the system. Another thing, you know, we hear that we really want, you know, 2 years of membrane life, but we're only getting 9 months, and so and the impact of that is that, you know, we have increased downtime, whether that's from cleaning too frequently, whether it's replacing elements more frequently than we want to, and it's increased costs. And you know, one of the ways that we look at it is, you know, are we operating at the right pressure? Do we have the right operating parameters? Has there been an upset? And one of the most common upsets that we see in the industry is when either on a startup or after a clean in place, we would have a pressure surge or a water hammer that can cause either a seal breach or an element defect. And so one of the ways to prevent that is having a VFD or soft start on the pump. And, you know, every operator, you know, if we're using manual valves and, you know, you tell open up the valve very, very slowly. Well, you know, the operators, they've got 1,000 things to do that are on their plate. So, you know, any time that they can save a little bit of time to move on to the next test, they'll do it. And that's, you know, what part of what they're trained to do. But one opening up a valve too quickly can ruin a bank of elements. And so we want to make sure that, you know, anything that we can do to eliminate the potential for upsets is there. So if we can, you know, like I said, if we have a VFD or soft start on the pump, that really prevents some of these upsets from and that cause element damage. And last one we hear, you know, is contamination, you know, bacteria in the paint tank, and it's decreased permeate water, coating defects, you know, and really the potential root cause can be an unstable bath, you know, or introduction of bacteria somewhere. You know, a lot of cases, you know, you have to do the special procedure to eliminate the bacteria, you know, with biocide and then filtration to remove the cells from the bath. So really, you know, what we want to do is, you know, look at options where there can be bacteria introduced, but also have, you know, very clear indicators and you know, as quickly as we can identify bacteria in the paint bath, we can identify it and then be proactive. You know, either clean the membranes proactively, introduce a high pH clean to help with the bacteria, maybe even a chlorine clean to kill the bacteria. So, you know, really, it's, you know, we know that upsets we're always going to have them, but it's how we react to them and how prepared we are for the upsets to be able to react to them. So talked a little bit about, you know, membrane essentials. It's a good, you know, are there any questions? Is there any questions that we see here?
Ben, there was a question on, can you repeat the temperature and the pressure ranges?
Yeah, so typically, I mean, the temperature and pH ranges are going to be more controlled by the paint bath and the specifications from the paint supplier. Now, typically in a paint bath, you're going to have 90 to 100 degrees Fahrenheit in there, and the pH is going to be probably between 4 to 5. Because there's going to be quite a bit of acid in the paint bath. So that's going to be pretty common. The membranes themselves, they can go up to max temperature of about 122 degrees Fahrenheit, 50 degrees C, and max pressure of about 70 psi for the elements themselves. And the pH, it can go up to about anywhere we can clean from 2 to 11.5. On the pH scale. In operation, the membranes can handle about 4 to 10 in consistent operation. All right, well, I'm going to move into the second part, which is total cost of ownership. And when we're looking at the process, we want to take a holistic view of the process and understand, what are the top priorities and how can our solutions impact those priorities. And we talked about the business drivers early on. Well, we even honed in, a little bit more specific here. And the 4 main factors are, looking to increase efficiency, product quality, sustainability, and safety and reliability. So even if we're focusing on those 4 business drivers, there's a big impact to have. But taking a little step back to understand total cost of ownership and what we're talking about when we say total cost of ownership, and really it's understanding that there's a number of hidden costs below the surface that may not be as obvious than say like the purchase price. Purchase price is very straight, clear. It's the element is this cost, and that's how much we're going to be paying a year. However, there's a lot of costs underneath the surface that may impact that purchase price and change the total cost of ownership. So one of that is risk management and safety. When we change from one technology to another, how are we managing the risk of that new process? Is there safety considerations that we need to take into account? Training. Our operators have been using the same technology for 15, 20 years. They're used to it. If we bring in new technology, how much does it cost to bring our operators up to speed on the training aspect of it? Labor. How is the labor impacted? Is it save labor? Is it more laborious in cases? Installation costs. If we have a new technology, we have to take into account the capital and the installation costs associated with it. Consumables, it may not be the same cleaning formulations. It may be different concentrations. So we want to make sure that we're taking that into account. Unplanned downtime, are the elements being replaced more frequently, less frequently? Do we need to clean more frequently? So these are some of the things that we're taking into account, and maintenance costs and replacement costs are a part of that as well. But really, it's the point of this is that purchase price is really only 25% of the equation, and if we're just looking at purchase price to make decisions, it's going to potentially impact and cost money down the road if we're not considering all the hidden costs associated with it. So when we're looking at ultrafiltration in particular, these are some of the considerations that we have. So the element, the cleaning chemicals, the labor, utilities, the quality, water use, wastewater produced, and the downtime. And really, you have to coming into this, there's process steps before the UF, and there's process steps after the UF. And you can't just optimize based on one process step. We have to ensure that whatever is being optimized and where we want to focus on, it's not going to impact the upstream or downstream processes. This is a part of a cog in the entire process, and we want to make sure that we're evaluating the entire process, and any change that we make, understand the impacts of both upstream and downstream. And really, because of this, are the costs created equally? When you break it down, and I'll go through an example here in the next slides. It shows that not all these costs are equal. Some of them are much more important and much more impactful on the P&L than others. But the goal will be to optimize it so that we're making the best overall decision from a process economic standpoint. So when we're talking about that, one of the common things is element replacement, and when we're focused on UF, we got to ask ourselves, what are the costs associated with different element replacement schedules? And the common thought is, hey, if we're replacing elements, if we extend the life of them as long as possible, that's going to be our best economic decision. That's going to be the best economic operation. And that may be the case if you're only looking at purchase price alone. And that's what the chart shows. If you're just looking at the element replacement costs, it's obvious that we want to maximize the membrane length. We want to get to that 18-month element replacement, because it's a third of the cost of a 6-month replacement. But really, we got to ask ourselves, well, what is triggering this element replacement? What is causing us to make these decisions? And why are the elements typically replaced? And so if we understand that, and we tie that back to the process economics, we can make the best economic decision by laying out all the parameters. And so, element cost is a big part of it, but there's also a number of other constituents that we want to look at: energy costs, chemical costs, water costs, wastewater costs, downtime, paint loss. There's all these considerations that we need to evaluate to make sure that we are making the best decision. And so when we're looking at the initial phase, we see, if you just look at element costs, yep, best decision 18 months. It's a third of the cost. That's the way we should go. But when you consider energy, that as you're running these elements for 18 months, the energy is going to increase, because you're going to have a little bit more driving force to push the water through the membrane to create enough rinse water for the process. In order to last 18 months, you may have to perform more chemical cleans. So at the 6-month cycle, you may not be cleaning at all. You can just run for 6 months and then replace the elements. At 12 months, you may be cleaning every month or so. Well, at 18 months, we want to make sure that we're not, impacting, you're not embedding the foulant into the membrane. So we need to clean a little bit more frequently, which increases the chemical costs. Water costs, once again, with increased CIPs, you're going to have increased water costs as well. And same with wastewater generation, with increased CIP. And then, how that impacts downtime, it's that's going to impact the costs. And then if we have any paint loss, that's going to impact the costs. In this case, we kind of said the downtime and paint loss were equivalent, but something that we want to take into account. And if you add up all the numbers, in this case, it made sense to replace elements every 12 months. That was the best decision economically. And you see, if you're looking at the total annual spend for the 3 options, it just happened that the 12 months was the most optimal element replacement time. And so, but we wouldn't really understand this unless we took into account all the costs of operation and optimize the total cost of operation. What we once thought was 18 months was the best change out time. Well, that turns out to be the most expensive total cost of operation aspect in this example. So, this isn't applicable to every plant. It's not like, 12 months is the best, element replacement decision. But what we want to share is that you got to make sure that you're understanding your plant, you're under operation, and that you're evaluating all the process economics to make sure that we're making the best replacement decision. And then in addition to this, it provides a benefit that we can be a little bit more proactive in making replacement decisions. A lot of the times I see plants that, the 8-inch element, it's dropped below 1 gallon per minute, it's time to replace. Well, but that's pretty conventional, typical way of thinking, but that's being a little bit reactive. And if you don't have the element on the shelf, how much impact does that have of the lead time getting the elements to site? Where if you know that, hey, at 12 months, we're going to be replacing the element, because we know that's the best economic decision, a month ahead, we can ensure that we have all the parts on hand, and so that we're prepared to make that swap out and make it as efficient as possible. So we're not scrambling at that time. So going into a couple case studies that show, kind of this TCO at work with specific clients. So in this case, we had a parts coder that they were wanting to increase their line speed by 50% because they wanted to increase their revenue by 30%. And so, they boosted up their line speed, and when they did the analysis, they realized that their constraint was going to be rinse water. So the plant manager found Solecta at actually a conference, and in collaboration with the client, we basically took our latest UF technology and replaced their 4-inch element system. So they had 16 4-inch drop-in elements, and we replaced that in collaboration with them with 5 unit design modules. And the unit design is an integrated element and housing in one. And so really there was a number of benefits from implementing this new technology from Solecta. And number one was they were able to produce the rinse water in the same footprint that they had initially. So they with a 4-inch bank, they were really constrained on space, and so if they were just going to add 4-inch elements to the end of that bank, they didn't have the space to do that. So by implementing the newer high area module, they were able to reduce 16 elements to 5, and basically produce more flow from a smaller footprint. And what that allowed them to do was make their rinse water in that footprint. And so in addition to that, because they didn't have to change out 16 elements and they were down to 5, number one, the downtime was decreased. So the uptime and parts coding time, uptime was increased. And we also decreased the element changeout time by 92%. So that was a big impact to them. From a planet perspective, from a sustainability, we were able to lower the energy demand per gallon of permeate produced. Also while increasing the permeate flow while reducing the overall footprint. And then the last aspect of this was, with the unit design, there's much fewer seals, so there's much fewer chances for leaking. And if there is a leak, it saves on troubleshooting time. But really, we were able to decrease increase permeate production of 69%, which met their goal of 50%. So, the bottom line is they were able to meet their 30% revenue increase with the help of our solutions. Next case study, we'll go over to Europe, and where a large automobile manufacturer in their ecoat process, they needed to improve their legacy flat sheet system. In addition, they wanted to eliminate the chlorine cleaning aspect. So in Europe, they want to reduce the chemicals and specifically reduce any chlorine that's used in the process. So once again, in collaboration with the client, we installed the unit design modular system to replace the legacy flat sheet system. And in doing this, we completely eliminated their need for chemical cleaning. So they were cleaning 4 times a year, and with the optimization of the parameters and the paint bath, we were able to eliminate cleaning altogether. In addition, we were able to reduce energy demand because we were going to a more efficient process from a flat sheet UF system to a spiral wound UF system. So really the benefit here, where we eliminated the 4 cleanings per year, completely eliminated chlorine from the process, 20 cubic meters of fresh water for cleaning saved, and then a 10 kilowatt hour per hour energy reduction. And when you put that into financial terms, it was an overall benefit of $114,000 a year for them. And this is what it came down to. There was $26,000 in energy savings, $80,000 in chemical savings. And then we even reduced the cost of the membrane system by about $8,000 a year. So even though, you know, if we're focused on the membrane alone, you know, there was savings there, but it was a small part of the overall savings of the process when you're looking at energy and water as well. So, you know, where else can this TCO methodology help guide decisions, and where else can we apply some of our solutions further in ecoat? So, you know, we look at the final rinse, and right now the typical final rinse is using an RO or DI system, and it's really the only freshwater requirement in the ecoat process. So, you know, basically when the final rinses come in, you use it maybe once or twice pass through, but then it goes to wastewater. So, you know, with a FR, you're having a high freshwater requirement, a large wastewater requirement. And so is there a way that we can improve that process from a sustainability point of view? So when we're looking at the final rinse solution, you know, the four main drivers to start off were it was freshwater savings, wastewater reduction, energy reduction, and there was a regulatory aspect as well, as countries from around the world start changing their wastewater requirements and getting tighter on and more stringent on wastewater requirements and discharge requirements. The FR is a solution that can help mitigate those concerns. So in this case, you know, there was a large client that wanted to reduce their fresh DI water consumption without jeopardizing the final product quality. And really what we were able to do is from a holistic point of view, look at the process and really develop a new product that works in this process to really make this an entire closed loop system. And one of the concerns with RO DI water and sending it back to the paint tank, it's actually too good a quality. You're going to upset the paint bath stability if you're putting too clean of water back into the paint tank. And so what this FR membrane does, it allows some of the solvent to remain in the permeate, which does not impact the rinse water. But it allows it to be a closed loop system and recover some of those paint solids as well. And so with this FR system, really we eliminated the need and manpower for weekly clean water change out. So this involved the DI regeneration and then just the weekly maintenance on the DI system. And they were doing basically once a week at the site. And really what it amounted to once we implemented the FR solution, they were able to eliminate almost 35,000 tons a year of clean DI water consumption. So, I mean, that corresponds to about $225,000 a year, a little bit more than $225,000 a year in DI water costs alone. And in this site, they were actually wasting quite a bit of paint in the final rinse, so they weren't getting quite a good rinse off. And so when they were in the final rinse, they were wasting quite a bit of paint there and sending it to wastewater. And so in implementing the final rinse, we're able to return that paint back to the closed loop system. And that was an impact of about $135,000 per year. So the net was over $275,000 in savings, and you know there was a little bit of capital that was required for this, but you know it was less than a 9-month return on investment for this FR system. And you know, getting into a little bit more of the details. So you know there was the cost of the FR membrane, a little bit higher electrical costs, but the savings on the freshwater and paint costs really outweighed any of the extra costs, you know, yielding that $275,000 in savings. So just to, you know, give you a visual of what that looks like. On the left picture is UF permeate. You know, it's a good quality water for rinse water for the initial rinses, but doesn't meet the requirement for the final rinse. The total solids is about 0.6%. And so if you were to use this in the final rinse, you'd have issues with coating quality. Where on the beaker on the right hand picture, that shows the FR permeate, and we're at total solids of less than 0.01% and pH 5.3. that does meet the requirements for the rinse water. And you know, we've talked to paint companies, and anywhere less than 0.1% is good and a good quality water for the final rinse. And you know, the highest we've seen coming out of the FR membrane has been about 0.06, 0.07%, so well below the requirement for the FR for the final rinse process. So coming back up to a high level wrap up, so total cost of ownership not only evaluates the purchase price, but it looks at all the other costs. And how is the pie chart on the left, how does that change based on each different plant? And each plant is going to be different. You know, each plant has their own priorities. They all have their unique processes. But really, it's evaluating what the business drivers are, what the goals are, what the priorities are, and tailoring a solution to meet those priorities and goals. And you know, balancing that pie chart so it makes sense and meets the priorities of the clients. And you know, are there other costs and scenarios that should be considered? You know, how is this impacting the downstream processes? You know, is the pretreatment required? You know, something that is causing issues, you know, where we have to have more bag filter changeouts. You know, some of those may happen, but what it comes back to is let's evaluate this from a process economics point of view, and let's make the best decisions from an economic point of view. So, you know, taking, you know, total cost of ownership and how that ties back to what Rasch and Solecta delivers, and really, you know, we're delivering the products to make these solutions possible. But it's really, it's not just about the product, it's about tying the product to the application's expertise that Rasch and Solecta can provide. So, you know, on the right is the unit design, which I talked about a number of times. It's the element and housing in one, where you just attach the end caps to the rack. Makes it very easy for replacing elements, very high low footprint requirement for these. So, you know, these are specifically designed for ecoat applications for this. But, you know, if, you know, there are other spirals that exist, we're able to retrofit many other spirals. And when we're doing that, we always want to do a plant audit to make sure that the operating parameters are within range. You know, many of the products are very similar, but we want to optimize the operating parameters for selected products. And, you know, there's product differentiation. You know, we try to make things as easy as possible on the client and eliminate any potential defects or hardships. And so, you know, on the unit design, we don't have a permeate plug in the bottom end cap. So we actually have a glued plug in the bottom of our unit design. Eliminates some seals, makes it easier to install, as you only have to be connected to one adapter on the end cap. They're easy to replace and long and stable life. You know, we have, with a paint bath monitored and healthy, we've seen elements last 2 to 3 years with the unit design. And then number 4, you know, the applications expertise and customer experience, whether that comes from training, system design, you know, anything. If you guys have challenges, problems, you know, reach out to Rasch, reach out to us. You know, we're always available to help provide the solution to a challenge. And with that, we'll wrap it up. Here's, you know, contact information for me, and feel free to reach out at any time. So with that, well, you know, thank you for your time, and you know, we can open up for any questions now that we have.
Ben, there's a question in the chat. What sizes of elements do you offer?
Yeah, so really good question. So we offer anywhere from 4-inch all the way up to 10-inch unit design, and a number of configurations in between. So the most common sizes in ecoat are going to be 4-inch diameter, 5.6-inch diameter, 7.6-inch diameter, and then the modular units. But we do have a number of configurations within those sizes.
Were there any other questions?
Well, great. Well, Should I throw it back to Alejandro to conclude?
Yes. Ok. En un momento determinado, después de la presentación, si de momento no tuvieran ninguna pregunta, se pueden hacer posteriormente, nos mandan sus preguntas o cuestiones por correo y se las respondemos. Y la otra opción es, cuando vayamos a hacer visitas a sus plantas, podemos darle respuesta a sus dudas. En un momento dado le están presentando un cuestionario con algunas preguntas en referencia a dudas que llegaran a tener. ¿Alguna pregunta que tuvieran?
No, Don Alejandro, for me it's very good. Thank you, Don Alejandro. Thank you, Ben.
Ingeniero Campuzano.
En mi caso, todo muy claro. Gracias por la presentación.
There is a question, Ben, can the membranes be washed with acetic acid?
Yeah, absolutely. Acetic acid is a common cleaning chemical. So what I can send Alejandro all of our cleaning recipes. There we have about 4 or 5 different recipes depending on the degree of fouling and the type of foulant that's used in ecoat. So I can send those to Alejandro and he can distribute for anyone on the call.
Pues, ahora el punto es, como les comentaba, en un momento dado las dudas que llegaran a tener, no es el momento en que tenemos la presentación y ya no se pudiera dar respuesta, ¿no? O sea, siempre vamos a estar abiertos a las dudas o preguntas que tengan, y por igual, en un momento dado se les hace el ofrecimiento de cuando requieran capacitación para su gente, nada más es de que nos pongamos de acuerdo y lo podemos realizar en su planta, para que la gente conozca el manejo y las características de los procesos o sistemas que tienen instalados en sus sistemas de pintura.
There's another question.
Sí, Araceli.
Let me see here.
Alejandro, tenemos otra pregunta.
How much backwashing over a lifespan?
Sí.
Ben, the question is, once its lifespan is over, can the membrane be recovered with backwashing?
Yeah, so you never want to backwash a spiral wound element. And when I mean backwash, I mean flow from the permeate to the feed side. So there is a way, you can reverse clean, which is bringing the flow from the concentrate to the feed. So we're staying on the same side of the membrane, but you never want to backwash from the permeate to the feed side. You can damage the membrane and delaminate it. But there is an option for reverse cleaning, which means you bring in the feed flow to the concentrate side, the top side of the element on the feed side, and then do it that way. At the end of life, I mean, you kind of hear stories about people flipping the element over at the end of life and getting a little bit more life out of it. It can be done. I think it's probably more effort than what it's worth. It's in actual practice. You're not going to get it. It's not going to recover drastically when you flip it over. But I have seen people extend life for a couple weeks out of that. So max temperature for the backwash, I see that one. So like I said, we don't want to backwash from permeate to feed, but you can do a clean with just permeate quality water if you're introducing on the feed side. And the max temperature for that would be 122 degrees Fahrenheit or 50 degrees C.
Ben, in the case of the temperature, usually the product what we use is paint. No? I think that the maximum temperature depends the paint. No.
Yeah, in operation, it's going to determine on the paint, but there are systems out there that will have a clean in place system that they can heat their cleaning formulas separate from the paint solution. And so if you have a separate CIP system, you can elevate the temperature further than what's in the paint bath. But you don't want to introduce that to the paint bath. So typically the cleans are done at similar temperatures to the paint bath to make sure that we're not upsetting the paint bath. But from the membrane perspective, it can tolerate a little bit higher temperature than that.
Ben, there's one more question. Are the conditions the same in the last rinse? I'm assuming it's a final rinse.
So they will be, the FR operation will be different than the UF operation. The pressures are going to be different. The cleaning frequencies are going to be different. Cleaning chemicals are similar, but there are going to be process differences between the FR and UF.
Okay.
Next one was, does Solecta have chemicals for cleaning the membranes?
So we have cleaning protocols, but all of our cleaning protocols use generic chemicals. We don't recommend any specific cleaning chemical other than generics. So we don't supply the cleaning chemicals, but if there's a need, either Alejandro can point you in the right direction, or we can make recommendations for procuring the proper chemicals. But our recommendations all use kind of generic type chemicals, nothing proprietary.
Pues el punto es pues agradecerles su tiempo para esta presentación, ¿sí? Y como les comentaba anteriormente, en un momento dado seguimos en contacto para lo que requieran, ¿sí? Pues bueno, thank you, Ben.
All right, thank you, everybody.
Gracias.
Appreciate your time.
Thank you, Ben.
Yes.
Absolutely, anytime.
Thank you, Ben. Thank you, Alejandro.
Have a great day, everybody.
Bye.
Bye.
Thank you,
Bye-bye.
guys. Bye-bye.